Hello there, and welcome to Forces 2, Part 1. So this is going to be the content that's going to be on paper number 2 in physics. And the first lesson is going to be on displacement, speed, and velocity. It looks like there's a lot of content in this, but there's actually not a lot. So just follow along. It should be a fairly straightforward video, and just be making sure that you're annotating as we go along here. You're going to start with the do now. 8 questions has a lot to do with what we did in Forces Part 1. So go ahead, pause the video, and do that. All right, so let's show you the answers. Make sure you have the correct ones. Make sure you're marking in the ones that you missed and the ones that you got wrong, and you have the correct answers there. With this lesson, we're going to be looking at just two things here, distance and displacement, and that's actually going to lead us to look at things like speed and velocity as well. So already you should be thinking about things like vectors and scalars and the such, and that's kind of why I say that this video is very straightforward, because we're only looking at the two things, and there is a new equation that is introduced, but it's not going to be very complicated. Looking at displacement and distance, first we're going to make sure that we understand what they actually are. So distance is how far an object moves, and it doesn't involve any direction. Whereas displacement, on the other hand, is it includes both the distance and where the object goes. And from there, you should be able to tell me that because distance is how far an object moves, so it's a measurement, but it doesn't involve direction, then you should be able to tell me that distance is a scalar and displacement is a vector, right? And I put on the site there what a scalar is and what a vector is, just to remind you what they are, all right? So we're going to look at the example for distance. It says, example, for a car journey, the distance is how much ground the car has covered, regardless of the direction changes that may have occurred during the journey. So if you've ever driven a car, you'll know that on the dash, there's a really big number, right? It might say like 20,000 miles or it's basically the amount of miles that car has driven over its lifetime. Okay, so when it was first manufactured, that reading was at 0. And then every single mile after that was recorded onto the car. But obviously you don't know which direction that you were driving, and so that's kind of your distance. This is actually really helpful because if you're buying a car, you want a car that has very low mileage, because that means that that car has been driven very much. So it's a good indicator for how far your car has traveled. For displacement, this is something that we use a lot less, and that is displacement can be seen as basically how far from your original position were you. So for instance, if let's look at figure 1 and 2, right? So the one on the left, you'd be able to really simply tell me, well, the distance in that one, okay, would be somewhere, it says around 9 meters, okay? And so basically what you did, if you took that line that goes from A to B and you straighten it out, you would get 9 meters. And that's how much distance you traveled. Doesn't take into account for any direction changes and stuff like that. But if you look at figure 2, it's very straightforward. It goes from A to B, it's a straight line. And that would be your displacement, okay? The sentence at the very bottom there, it says displacement can be thought of as how far out of place an object is compared to its starting position. So displacement only occurs when you have an object that moves away from its original position. If, for instance, you had an object that went from A to B and back to A, you would actually have zero displacement at all, because the object that we're looking at hasn't moved away from its starting position. Okay, but you do, with questions like these, you do have to look at the question itself and really read them specifically for whatever situation that they're in. All right. And that brings us to the first two checkpoint questions. Pause the video and make sure you answer these, and that way we know that you understand what you've just been told. For the first one, it says, does a distance quantity require a specific direction? For example, is it scalar or vector? And this one is, no, distance is a scalar quantity, so you do not need a specific direction. The next checkpoint question is what I was talking about at the end of the previous slide, and that was if an object moves 3 meters to the left and then 3 meters back to its initial position, what is the object's total displacement? Okay, and that one, your answer should be 0, because the object did not go away from their original or initial position. So this is what I mean by you have to read the questions very carefully, and you have to understand what they're actually telling you in terms of what information has been given in the question. All right, now looking at an exam style question, we have a train that travels from A to B, and there's your diagram there. So figure 1 shows the route taken by the train, and it's been drawn to scale. All right, and this is going to become important for part B. It says, for the first part, it says the distance that the train travels between A and B is not the same as the displacement of the train. What is the difference between distance and displacement? So this one is very straightforward. I'll let you pause the video really quick just to answer A, and then we'll answer B together. Right, at this point, if you answered question B, if you already answered it, that's fine. I'm just going to walk you through B. But for the answer for part A would be that distance is the amount traveled, where displacement is the amount the train has moved from its initial or original position. Okay, so that, again, that line, that curved line that goes from A to B, that is your distance, okay, because that's how much the train has actually traveled. Whereas the displacement would be if you drew a straight line from A to B, that would be your displacement. So for part B, if you want to pause the video really quick and answer part B, go ahead and do that. But it says that use figure 1 to determine the displacement of the train in traveling from A to B and show how you obtain your answer. Now this is going to be a bit tricky because what I'm showing you on the board might be different from what is actually on your paper. But how you answer this is you're going to basically get a ruler to measure a line that goes from A to B. All right, so I've drawn a green line that goes from A to B, and that is essentially your displacement. And what you're going to do is you're going to measure it, and you're going to tell me how many centimeters is that green line, okay, or whatever line that you have drawn on your paper. And this is one of those things where you really have to look at the question and get all the information that you possibly can. Because if you look at the bottom right corner of the diagram, or in figure 1, you can see that there's a scale, and the scale says 1 centimeter represents 5 kilometers. And what this means is every centimeter that you have on that green line represents 5 kilometers in real life. So think about figure 1 as if it were a map, right? A map doesn't actually show you really how far things are. And so what they have to do, if you make a map, is you have to create a scale. And the scale tells you generally how far things are. All right? So using that method, you measure the line between A and B. And this is where I'm going to say it might differ because what I have on the screen here might be different from what you have on your paper. So depending on how you measured it, okay, because you might be off by 0.1 or 1 centimeter, which is fine. Okay, what you were going to do is, for example, if I measured out that that line is 5 centimeters, then what you would do is you would multiply it by 5 because 1 centimeter is 5 kilometers. Okay, so 5 kilometers for every centimeter to get 25 kilometers. That's your displacement, all right, the actual displacement of this train. And since we're talking about a displacement, we always have to add a direction, and they do add north in the diagram, okay, in figure 1, so north is pointing straight up, and since the displacement is going slightly to the right, we're going to call that northeast, right? So it does pay a little bit to know your directional your directions, north, south, east, and west. Okay. Okay, so now that we looked at distance and displacement, we can look at the next two things that correlate very nicely with those, which is speed and velocity. So in your head, you might think that speed and velocity are the exact same thing, and you wouldn't be too far from the truth. We have looked at speed and velocity before, and hopefully you remember some of this. But we know that speed is a scalar quantity, which means that it's just a number. It doesn't include a direction on where it goes, right? It's just how fast are you going. And speed can be thought of as the rate at which an object covers distance. Okay, so speed and distance are directly correlated there. And so if you're looking at figure 1, right, the same diagram that we looked at on the first page there, if an object traveled between A and B in 1 second, right? And remember that was 9 meters. Then we could say that it has an average speed of 9 meters. And I'll explain what average speed actually is in a couple slides because we're going to look at a little bit more practice with that. So that's your speed. If we're talking about velocity, all right, velocity of an object is its speed in a given direction. So velocity is a vector quantity, so that should be easy to remember, vector velocity. And velocity is the rate of change of displacement and is equivalent to an object's speed in a given direction. So here's where it gets a little bit confusing because velocity and speed can essentially be the same thing, except that velocity has to have a given direction. All right, that's why it says it is equivalent to an object's speed in a given direction. Okay. So for the journey from A to B, because the direction is constantly changing, the velocity would also be constantly changing as well. Because we're looking at magnitude and direction, if the magnitude isn't changing, if it's constant, then you could say the velocity is the same. But since the direction is not constant, since the direction is constantly changing, then we would say that the velocity is also changing as well. And last thing that you should know is that the SI units for speed and velocity, since they're both essentially the same thing, is meters per second. So anything outside of that is not SI units, and it all depends on whether or not you can convert it or not. Because sometimes they might give you a question where they give you miles and hours, and you wouldn't really have the capacity to convert miles into meters. Okay. Just to finish this off, I just have a small diagram here that really quickly explains what the difference is. So if you have a train that covers a distance of 550 meters in 10 seconds, then your speed for that would be whatever the distance was traveled over the time it took, which is 550 over 10 seconds, and you get a speed of 55 meters per second. All right. The displacement is essentially the same thing, but we've specified that it's going east. So then it would be 55 meters per second east. And for this example, because I haven't specified that the train is turning and moving directions, it's in a given direction, right? So it has to be equal to the speed that's given. All right, so let's look at some examples of speed. The speed of a moving object is rarely constant. All right, so if you walk, if you run, or travel in a car, your speed is constantly changing. All right, we're not robots that move in 4 directions, up, down, left, and right. We are always moving and we're always constantly changing our directions. And since we're changing our direction, that means our velocity or our speed is constantly changing as well. So there's lots of factors, age, fitness, terrain, distance, things like that. And it does help to kind of know what typical values are. So walking will take you 1.5 meters per second. Running, you might be traveling at a speed of 3 meters per second. And cycling, you might be traveling at 6 meters per second. I want you to take in a second and just sit down and understand how fast 6 meters per second or 3 meters per second actually is. Okay, think of a meter. All right, so we're going to look at running. Think of 3 meters. Okay, so it should be not a very far distance, but it should be enough to be like, okay, well, that's clearly something that's not as short as it should be. And now I want you to cover that 3 meters in 1 second. All right, and then do it again and again and again. So every second, if you're running at 3 meters per second, every second you are covering 3 meters. Okay, that's actually quite fast. And obviously for cycling, if you're on a bicycle, then you're going to be traveling a bit faster than if someone was running right next to you. So cycling, you're traveling at 6 meters per second. All right, so we say meters per second, and we actually are talking about a very, very fast speed. So we're going to look at taking average speed now. So average speed is the speed taken over a whole journey. And the key word here, or the key phrase, is going to be the whole journey. All right. And if you remember taking averages in maths or even in sciences, right? Average is just a central value from a list of numbers. You might be given 20 numbers, all different, right? And if they ask you to get the average of that, all you have to do is add them up and divide it by however many values there are. So for instance, if I wanted the average of a test score in a certain class and I have 30 students, then I would add up every student's test score okay, and divide it by 30. And so most averages might range from 50% to 80% or 90%. And from there, if I told you your average, then you can tell me, well, I was below average or I was above average. And if you're above average, that means you did better than a majority of the students in the class. Okay. Some other typical values that maybe you might want to know is that cars travel from 13 to 30 meters per second, which translates into 29 to 69 miles per hour. So if that if that kind of relates better to you, then you can think about how fast that is. And there are some other ones for a train, for an airplane. And in science, especially in physics, we're going to be working with things like the speed of sound. Right, or the speed of light. And so the speed of sound is actually quite slow if you compare it to other concepts. The speed of sound travels about 330 meters per second. But again, I want you to think about how fast that actually is, right? Think about how far 330 meters actually is, and then try and cover that in 1 second. All right, that's how fast sound travels. And you might think it's actually pretty instant, but if you think about the speed of light, the speed of light is extremely fast, all right? Extremely, extremely fast. And so light is much, much faster than sound, which is why, for instance, if you have a thunderstorm, you always see the lightning first before you hear the thunder. All right, so 3 really easy checkpoint questions. It's just asking what are the typical values for speeds for walking, running, and cycling. So I'll just give you a couple seconds to pause the video and go ahead and answer those. All right, simply 1.5 meters per second for walking, 3 meters per second for running, and 6 meters per second for cycling. Okay, very straightforward. Moving on. All right, so now we are given an actual equation for calculating speed. For an object moving at constant speed, the distance traveled in a specific time can be calculated using the following equation, and that is distance equals speed times time. All right. Now, this is the easy part of it, right, because it's all multiplied. And before I move on to the rearrangements, I want you to make sure that you understand what units we're talking about. And the only thing here that will be confusing is the distance. And for distance, we're using the symbol S, all right? Now, we're using S because we use the letter D for something else. But for this part, S actually means displacement. All right. And we use displacement because it's a lot easier just to be like, we're just using displacement because we know that displacement can be substituted for distance. You just take out the direction, right? Because distance doesn't take into account the direction. So that's why we use S. And I've put the triangle onto the left side there where you have S at the top and V and T at the bottom. And that's just to help you out if you need help rearranging equations. But looking on lines 1, 2, and 3 on the next page, you see that speed equals distance divided by time, and time equals distance divided by speed. So I've put that into a much easier format where you have V equals S over T, or T equals S over V. And I just like that visually because that way it kind of coincides with the triangle on the left much better in terms of if you cover up T, then you have S that is over V. All right. And I'm going to give you the same spiel again about rearranging equations. If you can, I strongly recommend that you memorize S equals V times T and then learn how to rearrange the equations. All right. At this point, I'm not sure if you've had lessons on rearranging equations, but if you go on YouTube and type in, GCSE how to rearrange equations, you'll get tons and tons of hits. This one is one that I found that was pretty simple and straightforward. Does a good job of explaining how you go from step to step. And so if you want to check that out to learn how to rearrange equations, go ahead and do that. Very, very helpful if you're able to do that. All right, so we've looked at average speed, right? Because that's by using the total distance traveled, so the whole journey, right? Divided by, and since we're looking at the whole journey, we're looking at the total time that it took. Okay, so that's your average speed. And the equation there is given, but that one is pretty straightforward because it's actually the same as the one from before, where if you have V equals S divided by T, right? So s is your distance, t is your time. So that's essentially what it is. Nothing really new there. And again, I'm going to change that into a format that looks a little bit better to your eyes. Speed equals distance over time. And that's why if you've ever driven a car, if you've ever been in a car, you'll see that there's a speedometer, right? And on there, it should have a bunch of numbers, and it might say miles per hour or it might say kilometers per hour. That's essentially the same thing that we're looking at here. That's your speed, right? So kilometers is a distance, and since it's divided by hours, which is a time, then you have distance over time, which gives you speed, right? And mph is the same thing, miles per hour, right? Miles is a distance, hour is a time. So that's where you get your speeds on a speedometer. Now, if we're looking at instantaneous speed, right, we're looking at the speed of an object at a very, very specific point in time, all right? And so the speedometer in your car actually gives you your instantaneous speed. And instantaneous just means that you're looking at a very specific point, right? Not over a total journey or anything like that, but just basically, if I froze time while you're driving a car, what would your car be traveling at, okay? And so you might think, if you look at the speedometer here, you'd say it's traveling at 55 miles per hour, right? That's your that's your instantaneous speed, okay? Specific location and time. All right, let's do some practice. All right, you have your equations from the previous sheet. So looking at the chart, you've seen lots of questions like these before where you're missing certain things and you just need to figure out, are you going to multiply them or are you going to divide them? So your first column is distance traveled, which is your S, speed is your V, and time is T. Okay, so if you want to label those, go ahead. I'll do the first two rows for you, and then you can do the rest of the chart. So distance traveled is missing. You have speed and you have time. So S equals V times T. So V is your speed, time is your T. So 5 times 12 would be 60. Exact same thing for the second row. S equals V times T. So 150 times 30 will give you 4,500. Now for the third one, okay, I'll show you how to do it. I want you to do it by yourself with your calculators. You're missing your speed, all right, but you're given your distance and your time. So V equals S divided by T. All right, so figure out which one's your S, which one's your T, and then divide S by T. All right, so for your third one, you should have gotten 125 because you divided 1,250 by 10. For your fourth row, same thing as the first two, you are multiplying. So you get 330 multiplied by 20, which gives you 6,600. And for the last one, same thing as your third row, you are dividing. Speed is distance over time, which is 4,200 divided by 70, which gives you 60. Okay. All right, so numbers 2, 3, and 4 on that page. Numbers 2 and 3 are pretty straightforward. Just be mindful that you are working in miles per hour, not meters per second. Whereas number 4 is a little bit more complicated. So I would like you to pause the video, go ahead and answer 2 and 3. Try and answer 4 if you can. All right, because I'm going to go over 2 and 3 and then I'm going to go straight into 4 right away. So go ahead and pause the video. All right, so a car travels 30 miles in 2 hours. What is its speed? So if you've been following a lot of my videos, you know that when you answer questions like these, you can either highlight or underline the numbers that are given to you. But since we're working with a fairly simple equation here, I'm not going to do that. But what you are going to do is tell me what equation that you're using. So the question is asking, what is the speed? And speed is v, so your equation should always start with v equals, and then you figure out the rest of the equation. So v equals distance over time. So I've accidentally used d, probably out of just reflex. That should be an s. So whenever you see a d there, can you please just change that to an s? And all you have to do is replace the numbers, right? So your distance is 30 miles and your time is 2 hours, so you're going to get 30 divided by 2, which gives you a speed of 15 miles per hour. Number 3, an aeroplane traveled 2,000 miles in 4 hours, so exactly the same thing. You have your equation v equals s over t, and you just have to substitute the numbers into the symbols. So your distance was 2,000 miles divided by 4 hours, and that should give you, same thing, 500 miles per hour. All right. So it's questions like these, they don't expect you to convert any numbers if the numbers given to you were already in miles. All right. And that's typically how we measure speed when we're using miles, is miles per hour. We rarely say miles per second. All right, number 4. So the winner of the Tour de France in 2018 completed the distance of 3,349 kilometers, which is the same as 3,349,000 meters, in a time of 83 hours, 17 minutes, and 3 seconds. So you're going to want to convert that to seconds. Calculate their average speed. So same formula, V equals S divided by T. And in order to do this, so you already have your distance, which is the 3,349,000 meters. Okay, so that's your distance. Now it's a problem with the converting the time to seconds, because you have to convert all that 83 hours, 17 minutes, and 3 seconds into seconds. And the best way to do this is basically just chunking it, right? So convert 83 hours into seconds, convert 17 minutes into seconds. The 3 seconds is already seconds, and then add them all up together. Okay, that's how I would do it, and I think that's probably the easiest way to do it. So 83 hours you can change into 4,980 minutes, which you can then change into 298,800 seconds. So that's 83 hours. 17 minutes, you can change that into seconds by multiplying it by 60, right? Because there's 60 seconds in a minute, and you get 1,020 seconds. All right. So this is one of those skills that you do need when you are converting units. So you should be able to convert minutes, hours into seconds, all right, even days. So the way that I converted hours into minutes is obviously multiplying it by 60, because there's 60 minutes in an hour, and then I just multiply by 60 again to convert it from minutes to seconds. All right. So once you have all that, you just add them all up together. So 298,800 plus 1,020, and don't forget the 3 seconds. So when you put all that together, you get 3,349,000 divided by whatever all that added up was. Okay, and you should get an answer of 11.17 miles per hour. Okay. Oh, sorry. No, that should say meters per second. My apologies. That should say meters per second. And we're going to continue on to 5, 6, and 7, okay? The 2018 British Grand Prix was won in a time of 1 hour, 27 minutes, and 29 seconds. The track at Silverstone is 5.891 kilometers, and the race is 52 laps. Calculate the average speed of the winner. And so convert time to seconds and distance to meters. So from there, you should be able to realize that your answer will be in meters per second. And so let's start off by converting what we know. 1 hour is 27 minutes and 29 seconds. So we need to convert that into seconds. You're going to use the exact same strategy as we did before. Just chunk it. So change the hour, change the minutes, and keep the seconds, right? So 1 hour is 3,600 seconds, right? So multiply it by 60, multiply it by 60 again to get seconds. And then 27 minutes, you just multiply it by 60 to get 1,620 seconds. And add the 29 seconds at the end there, okay? And you should get your total time. For your distance, right, you have 5.891 kilometers, and the race was 52 laps. So there's 2 ways that you can do this. You can convert the kilometers into meters first and then multiply by 52, or multiply by 52 first and then change all that into meters. Either way works, whatever one is easier for you. So I've done the second step, so I've multiplied 5.891 by 52, and so that'll give you the total distance that was traveled by the cars, right? Because if they traveled 5.891 kilometers 52 times, right, then they've traveled a total of 306 kilometers, and all you have to do is change that into meters, right? So changing kilometers into meters, again, is one of those skills that you need for converting, and to do that, you just multiply it by 1,000, because there are 1,000 meters in a kilometer. So you put that all together, and you have speed equals the distance over the total time. So there's your hour, 27 minutes, and 29 seconds. And you get an average speed of 152.48 meters per second. So that just means that whatever car that we're looking at here, the winning car, right, I believe, was traveling on average 152 meters per second. Okay, that's your average speed, or that was the average speed. Number 6, how long does it take a person to travel 5 meters if they're walking at 1.5 meters per second? So this one is very straightforward, very simple, but same thing. So now you're looking at how long does it take. So that's time, which means that your equation has to start with t. So t equals whatever fills in the rest, all right, which is s divided by v. Again, please ignore the d there. And now it's just a matter of replacing the symbols with the numbers. So distance was 5 meters, and the speed was 1.5 meters per second. So there you go. 5 divided by 1.5 gives you 3.33 repeating seconds. All right, so it would take you roughly just over 3 seconds to walk 5 meters if you're walking at a speed of 1.5 meters per second. That hopefully makes sense, okay? All right, number 7 requires you to watch a video of Usain Bolt. So Usain Bolt and teammates in I forget what year what year this was, but they broke 3 world records. So Usain Bolt ran solo for 100 meters and 200 meters, and then the third race was a relay race between 4 people, and they each ran 100 meters. So take a look at the video and put the times in the slots, right? And the second column there, and then what you have to do is calculate the speed for those 3 times. Okay, so go ahead and watch that clip. Right, so hopefully that was pretty fun to watch, just Usain Bolt defeating all those other runners. And here are the times that I was able to get from those. So the 100 meter he ran in just under 10 seconds, 200 was just under 20 seconds, and the relay race they won in 37 seconds. Now, each of these is quite simple. If you want the speed, you just get the distance divided by the time. So what you would do here is you would divide 100 meters by 9.68, 200 meters divided by 19.31, and for the third one, you'd have to do a total of 400 meters because that's the total distance that they ran, and divide that by 37 seconds. Okay, or sorry, 37.1 seconds. And the speeds that you should get are on the screen. And so this is actually a ridiculous speed because if you're looking at it, it's basically saying that Usain Bolt was running, for the first 2, he was running at 10, almost 10 meters per second. All right. So try and imagine how far 10 meters is and then try to run that in 1 second. Okay. That's what it means to be an Olympic runner. Okay. And then obviously for the relay race, it was even faster average speed because you've had lots of different people. Okay. Okay. Looking at the last page, this is higher tier, which means that you don't need to watch this slide. It's just one slide if you are not looking for higher tier. And what we're looking at is circular motion. Now this is actually pretty advanced physics here, so if you don't understand this right now, that's fine because unless you're going into A-level physics, you're not going to know too much about this. So let's just read along here. When an object moves in a circle at constant speed, its direction is constantly changing. That should make sense. Okay, looking at the picture below, if you're moving in a circle, all right, you can actually draw out the vector diagrams for where your forces are. So your green forces is actually the velocity, all right, and each one of those velocities is slightly different because the direction is changing. A change in direction causes a change in velocity, and you can actually demonstrate this because if you're running straight forward and someone asks you, okay, now run to the right, you're going to lose a bit of speed because you're changing your velocity. Okay, you cannot maintain the same velocity and change direction just like that. It's just humanly impossible. This is because velocity is a vector quantity. It has been associated, or sorry, it is an associated direction as well as a magnitude, so that's a vector. Examples of objects moving in a circle at constant speed but changing velocity can include a conker on a string, a car on a roundabout, and a satellite in orbit. So that's probably the most common one that you're going to see is orbiting. All right, but like I said, this is almost A-level physics, and once you actually understand the physics behind what keeps something in circular motion, like centripetal force, it does get a little bit more understandable. But the main thing that you need to understand from this is that when you have an object moving in a circular motion, the velocity is going to be constantly changing because the direction is changing as well. All right, so go ahead and try and answer that checkpoint question. You can use the same words as the text, but go ahead and pause the video and try that out. All right, so what I wrote here is an object moving in a circular motion at a constant speed has changing velocity, right? Straight from the text. This is because velocity is a vector quantity that depends on speed and direction. So even if your speed is the same, if you're constantly changing direction, then your velocity will actually change as well. All right. So moving on. And actually, that's the end of the lesson. There is a knowledge check at the end, 9 questions. 8 and 9 have to do with a little bit of chemistry. So go ahead and answer those questions, and I will reveal the answers in a second here. Perfect. So here they are. Make sure you're correcting them. Put down the correct answers. Hopefully, some of these you might have had to look back. For instance, numbers 5, 6, and 7 obviously are very, very specific questions, but they are in the text. So hopefully you do remember those. Most likely on a GCSE, they might actually give you some of these numbers instead of just trying to guess, well, how far does a typical person cycle, right? But there you go. And thanks for watching lesson 1, and I'll see you in the next one. Bye.